All right. Um, Hello everyone. My name is Daniel. I'm here to present the Software Development Trust for Loan to Raise. Uh, so this trust is a little bit different than the other trust. For I don't see any. I think there's maybe one or two that hasn't attended the midterms. But still, for if you're new here, the vision of this trust is to well, originally there's a change of vision, but then the original vision of this trust is to improve the extendability of L2R. Basically build a middleware system that can connect L2R to different simulator other than Arrival. And then basically unified and the deployment of L2R to different simulators. And then eventually we want to basically transfer L2R to the actual ROS system on racing car. Some of the design considerations, those are pretty similar to what we have as a team. I think the only one that we originally have, the one that's different is the extendability, where basically we want to extend the usage of L2R to not only what we have right now, but into different, as I mentioned, into different simulators, into ROS and stuff like that. Correctness and low latency are also mentioned by our previous thrust. Those are really easy to understand. So I'm just gonna go through this. Requirements. Well, for this thrust, we require RL agents, but we don't train them. We don't manipulate them in any way. Basically, we just have agents, and then we want to connect the agents into the training platforms. And we deal with all the software and stuff like that within the platforms. And there's a change, but then I'll get to that in a minute. Non-functional requirements, performance, usability, again, those are similar to what we have as a team. Extendability is the one we focus on. Basically, we want to extend the usage of the part. Terminology, I guess the different ones. So there's Carla, which I will be mentioning a little bit, and then there's the predictive safety filter that I'll also mention later. But all other stuff are all mentioned by our teammates. Plans. This was the plan we made in the beginning of the semester. There were changes to this plan, but then the original plan is to do the simulator connection, and then there's a latency reduction part. But then that one changed it into safety related issues. Right, yeah. Okay, so middleware structure. So this is, I think this is the start of the first half of the year, basically the spring semester from last year, where we kind of have this structure of L2R, and we want to build a middleware system that unify all the inputs and outputs, basically serve as a correspondent or serve as a middleman from our agents to the simulator. So right now, everything before the middleware, everything is connected, but singly connect, like everything in L2R is connected specifically to the rival simulator. And then we have a simulator controller, but then we basically create this middleware system where we want to unify all the inputs and outputs from the framework. And then depending on what type of simulator we're using, we do the data type transfer, we do all the messy works, data stuff. And then we connect to different simulators. And we're focusing especially on Carla because Carla is very popular, is widely used, and also is sponsored by Honda, I think. And eventually our mirror system could let us to connect to the actual onboard RS nodes, basically serve as a generalized connection piece that transmit data between the framework and the simulator or the actual car. And then instead of the simulator controller, we have the middleware controller, which has all the stuff I will mention later. But yeah, this will be the general structure of the middleware. In terms of implementation, basically we have on the left side, we have the connection, which is, let's say a simulator. On the right-hand side, we have the middleware, where it connects to, basically we have the middleware, and then we have left-hand connection. And then we have, those are parent class. And then we have separate classes for different type of input and output. For right now, we have the camera connection, the post connection, action connection. For the rival simulator, for Carla, there's more type of input and output that we can have. And then for the RS, we have totally different kind of classes. And then we connect them. Basically, we connect them using those convert function, where we convert a type of connection into the type of middleware, and then we connect them and transfer data using byte array. Right now, it's byte array. And we do that for each type of each type of simulator, or each type of the platform that we want to use. So basically, we will have ideally a lot of those type of connections, and we write basically we transfer different type of data, different information between them. This is the actual simulator. And then this wraps up the first half of the semester, first half of the year. And I think probably everybody, so as you can see, the background is black. So that's what I got from the previous presentation. So for this semester, there were a change in focus. We're no longer doing the middleware part, but it's similar. It has something to do with middleware that I will get to, but mainly focus on the safety lab, where we research the safe autonomous racing paper, and then we have a safety lab repo, and the predictive safety filter, which I will get into. Basically, safety lab has, I think the purpose of the safety lab, in my opinion, is ultimately to have the testing and validation of all the agents that are coming in, and it should be part of the middleware system. But right now, it has only one test, or it has only one like small part of the functions, which is the safety filter. But eventually, I think the goal is to make it a module that can test and validate all the agents, different agents that my teammates are working on. Okay, so predictive safety filter. What is that? So this is what this trust implemented for the safety module. And it is basically a backup plan that only kicks in when you're reaching an unsafe state. So in normal training of an agent, if you are, let's say, out of bounds, then you reach a constraint violation, and then you stop your training or stop your iteration, stop your stuff like that. And the safety filter is actually to deal with those kind of questions. So before you actually hit the bound, before you actually oversteer or understeer, it tries to predict what is going to happen, and then it will generate a backup control sequence that will lead the current state into a non-safe state. And they do that by solving all the constraints, the nonlinear constraints. And one of the things that is very important for safety filter is that it supports performance without very conservative interventions, meaning that, well, we definitely know that if you're about to, let's say, get out of the bounds, then you can just stop the car, but then it has a punitive term in its objective function that try to minimize the changes from the current thing you want to do, and then the safe thing you want. So basically, you have so if it detected that your current action is going to into an unsafe state, or is going to lead into a unsafe state in, let's say, 5 steps away, then it will try to find a other action that has the minimum distance of the current action you're about to take, which will lead you into a safe, known safe state. And also it is extended in real time. It doesn't need a bunch of training. It doesn't need very complicated machine learning models. It's just solving the constraints. And so it will, how it works is that it will analyze and detect unsafe control signals. So even if the signal is safe right now, if it detects that it will going to be lead you into an unsafe state in 5 or 10 steps, then it will still deem it as an unsafe signal. And then it will, as I said, modify the signal by finding a backup sequence that has the smallest distance from the current one you're about to take. Okay, so this is illustration of what this does. So if the current state, if it predicts that the current state or the current action you are about to take a state, then it will just change nothing about. So it will let the actual agent do its work. But if it detects a unsafe action about to take place, then it will kicks in, and then it will modify this unsafe control or unsafe state into a different kind of actions that will lead you into a safe state, as what I mentioned before. So as you can see, this state might not be unsafe. So it's not necessarily that this action will lead to unsafe states in the next iteration, but it will predict like 3 months or 5 steps into the future and see whether it's safe or not. And it does that by creating a lot of like safety constraints. And the objective function here, basically we want to minimize the change from the current action to the safe action. So we don't want it to be a drastic change. We want it to be as close as possible. And then it will also punish a very drastic maneuver. Basically, you don't want it to steer too much if it's going in a very high speed. As for the implementation, we have the nonlinear system, we have the constraints. As I mentioned before, as you can see here, basically it is just solving a bunch of the constraints. We have the dynamic constraints, we have input and state constraints, terminal constraints. So basically it's adding all those together, and then it's trying to solve a best option using the objective function. And as I mentioned, what this will do in the long term, I think, so all the agents might be different, but if you're using the same track, if we're using the same input and outputs, then the constraints could be the same. So it works on this agent, it works on this policy, then it could be hypothetically a testing and validating procedure for all the different kind of agents and policies that come from L2R. So basically all the policies and agents that my teammates is working, it could serve that. But right now, it's just standalone as a separate piece. All right. So that's basically wrap up the second part, where's the safety part. Reflections. I have a lot of say to a lot want to say to reference. So I think in my perspective, I think the time management part on my end is not ideal, I would say, just because there's a lot on my plate. But I think one of the things that I realized from the beginning of this capstone to the end of this capstone is that the documents and stand-ups actually helps you a lot. So if you are in the capstone classes, you know that most of the presentations, almost the slides that come from stand-ups. So stand-ups makes you make incremental steps to your final state or the final presentation. And then the documents are really helpful. Well, because it's organized your thoughts for the entire project. I didn't realize that from the beginning, but I think it will be very beneficial to the next iteration of this project, whatever the project you're working on. So for first year students, I think this is a very important lesson that I didn't realize back in the days. And also getting help. I think I can do better in seeking help for the project. And also if you don't like it, you can definitely ask for a change. I think that's all pretty cool with the course. So as advice to first year students. And here are my references, and that will be all. All right.
So can you say something about how much you implemented? So did you actually implement the predictive safety?
Yeah, so we have it's a part of the code up there. It's already like it's a separate file, it's already implemented. But then right now I'm working on how to incorporate that with the current SAR policy. So it requires a lot of like different inputs that we need to figure out for the current policy how to derive. For example, it requires like say for the terminal constraint, it requires a big matrix that can be put in as a constraint, as a subject to as a constraint for the solver. But how do you get those information? How do you compute this kind of matrix? It's a question when connecting this safety filter to the actual policy.
Okay, and then when exactly did you pivot to working on the predictive safety filter instead of just working on middleware in general?
I will say several weeks into this semester.
Okay. And then when you did that, did you do a detailed work breakdown and plan for everything that you were going to need to implement?
That's where I'll say I have a plan in mind, but not as detailed as the documents that we're required to provide for the first semester.
Okay.
Right.
And then do you think that's why you may have not estimated the amount of effort that would be required to actually implement and integrate and get some real evaluation?
Right. I think that is one of the that is one of the reasons I think. So that's why I think like a detailed planning would be really nice if you have
Anders, I had a question. How much of the Carla simulator connection did you implement?
So we have right. So I have all the classes I mentioned. It's all implemented, and then regarding to connecting to Carla, we have this kind of a modify. So original middleware has this kind of a dummy middleware in place when I take over, and then I created all the classes for the Carla and for the template for RS, but then the Carla stuff like that. But it's on my GitHub. Right. Yes. Mm-hmm.
And are you planning on having results for these safety filters?
I plan to have the result, but I'm still working on how to incorporate that into the current SAR agents and policies.
Okay, so I didn't quite hear the end of the answer about Carla. It sounded like we wrote the adapter classes, but it sounds like we didn't actually do any kind of end-to-end test with Carla.
I did do the end-to-end test, but then it's okay. Let me. I think I don't think it's actually went through, but I don't remember why. I think that was the end of the last semester.
Thanks.